Hello, my name is Peter Menocal. I'm the president and director of the Woods Hole Oceanographic Institution here on Cape Cod in Massachusetts. The Woods Hole Oceanographic Institution is the world's largest independent ocean research organization with over 1,000 staff. We have exceptional strength in ocean science and ocean technology and engineering, and we have operating large seagoing ships, submarines, and autonomous vehicles. So it's a large place focusing on oceans and ocean health. The independence of the institution really makes us unique in that we're very nimble. And in fact, the presentation I'll be giving you today focuses on an opportunity to understand the oceans with really focusing on how we can develop solutions for a warming planet. And indeed, that's the title of my talk today. So today, I'd just like to give an overview of how and why climate is changing, and really the vital role of the oceans. And a takeaway concept is really that the oceans are climate and the climate is the oceans. We will look at ocean-based climate solutions, and in particular, we'll be focusing on something called the Ocean Vital Signs Network. And this is a large multi-institutional focus on how we can develop an observational understanding for how to solve the climate crisis. So as we look to why the planet is warming, I think it's helpful just to kind of take a distance from the planet to watch a planet in transition. So this animation is really showing how the planet has warmed over the recent decades. And you can see this emergence of this color red, which is the warming anomaly due to global warming in our lifetimes. And indeed, by the time we get to the last slide of 2013, you see that there's red almost all over the planet. This is indeed the signal of global warming across the planet, which is now about 1.2 or 1.3 degrees centigrade warmer than the historical past. But a question remains for many people: what's really causing the warming? And this is one of the best examples I've ever seen of actually how we can decompose the observed global temperature warming that we're seeing from thermometers into what's really causing it. Is it due to changes in the Earth's orbit around the sun? Is it due to changes in solar activity? Is it due to volcanoes? And it turns out actually that all these factors play into the observed temperature changes, which are shown here in the black line. And so what we're going to do in this animation from Bloomberg is to break it down into different components. So in this case, we're seeing this blue line emerging of changes in the Earth's orbital variations around the sun. That's a 20,000-year cycle, has a very minimal effect on temperatures over the last century or so. Variations in solar activity, also not very important, but variations in volcanic activity, you can see there's some cooling events due to volcanoes that have cooled the planet. And you can see there's some resemblance between this and the black line, but it doesn't capture the recent warming. And then we can look at man-made factors such as land use changes, or changes in ozone concentration, which have a slight warming effect, or changes in aerosols. This is black carbon that's going into the atmosphere. It actually cools climate, or changes in greenhouse gases by themselves, and that warms up climate too much. And so if we look at all the man-made or anthropogenic factors influencing the temperature of the Earth, you see some warm and some cool the climate. All of them added together actually capture some of the warming that we're seeing today. But really, when you add in the natural and the anthropogenic, the man-made factors, we get a nearly perfect match between the temperatures that we observe and the temperatures that we can model using all these natural and anthropogenic changes. And this is how scientists know that there's a predominantly human influence on the warming trends that are happening right now. And in fact, fully 100% of the warming that we're seeing today is due to human activities. But the main thing is that when we actually look at the planet as a whole, where's all that warming going? And where we see the warming actually, where most of the warming coming from greenhouse gases is going, is into the oceans. The oceans are about 2/3 of the planet, and the oceans are actually absorbing and have absorbed about 90% of the excess heating from carbon dioxide increases in the atmosphere. And this is because the oceans are, of course, 2/3 of the planet in terms of surface area, but they're also very deep, and water has a very high heat capacity. And so the warming that's reached the surface of the ocean in some places now has actually gone all the way. The warming has actually reached all the way to the bottom of the oceans. And we can measure this through these autonomous robot pogo sticking up and down around the oceans around the world. And so this is one of the ways we can monitor how ocean warming is impacting the oceans more broadly. But just to give you an idea of, or to presage the future, this is a study that just came out this past year by actually a former postdoc of mine, Jessica Tierney. This is a reconstruction of global temperatures around the world since the last ice age. And so what you can see here on the left is that during the last ice age, global temperatures were colder on average by about 6 to 7 degrees centigrade. And that was, of course, because we had an ice age, 2 miles of ice over North America and another 1.5 miles of ice over Northern Europe. The world was obviously in a glacial condition. And then we warmed from 16,000 years to about 10,000 years, which actually coincides with the emergence of agriculture and civilization, into something called the Holocene period, the warm Holocene. And that's our time. That's when civilizations emerged around the world and developed. And so then when we look into the modern era, what's called the anthropogenic era, we can see that there's this continuation of that very flat warming trend, but then boom, in association with the emergence of the Industrial Revolution, we see this very sudden warming. And when we look at the forecast into the next century, you'll see this really marked rising of temperatures about 6 degrees up to 6 degrees centigrade warmer with a very high emission scenario into the future. We've already warmed, we've already seen warming of about 1.2 degrees centigrade. And so these futures really are another world that we haven't seen for more than tens of thousands of years, actually going back millions of years. So a question can be asked, what happens when you go into a warmer world like this? And again, we don't have an analog for this during the human era, but if we go back to the last time carbon dioxide levels were around 400 to 450 parts per million as they are today, that was about 3 million years ago in a time called the Pliocene. And so we can ask, what was the world like during the Pliocene when carbon dioxide levels were that high? And it turns out that you can drive along the coast of the eastern coast of the United States and crisscross over this little berm that's actually a former beach from 3 million years ago. And if you go up to that little berm, again, Route 95 crosses over this all the time. If you go up to that outcrop, and you can actually pluck out these beautiful seashells, in this case it's a scallop shell from one of these beaches. And this is along the entire coast of the US. The take-home point here is that this beach, this 3 million year old beach, which is a time when carbon dioxide levels were last at the levels that they are today, and will be into the future, was 75 feet higher than the current sea level today. So this is the Earth's equilibrium response to high CO2 levels. Basically, glaciers melt and it releases water back into the ocean, and that's what's elevating the oceans. So the reason why we're not looking at 75 feet of sea level today is because it takes a long time for ice sheets to come to equilibrium to that new warmer world. And indeed, we're just in the beginning of that right now. But this gives you an idea of why we're concerned about these warmer temperatures ahead. Another thing to keep in mind is that there are aspects of the warming that can be very abrupt and in some cases actually unanticipated. So some of you have heard about the Doomsday Glacier, the Thwaites Glacier in West Antarctica. The reason why we're concerned about the Thwaites Glacier is because we get this warming, as the oceans warm, they carry such heat capacity that they act like a blowtorch that can warm the ice sheets from below and melt the ice sheets from below. And that's shown by this red line here. And you can see that this is actually what's leading to the melting of the ice shelves in West Antarctica. That is the storyline behind the Doomsday Glacier. But the real concern is not so much the immediate melting of this ice shelf, but it's the big block of ice behind it. It's as if you're pulling a cork out of the bottle and you're allowing all the wine to flow out into the ocean, as it were. So that flowing of that wine in that case is really the flowing of the ice sheet that's been held in place by this ice shelf in West Antarctica. So this is the reason for the concern. And indeed, when we look at the most recent Intergovernmental Panel on Climate Change report, the AR6 report that came out last year, you will see this cluster of sea level rise estimates that are shown here in the various colors, the 8.5 to the 1.9 scenarios. These are different emission scenarios. The one that we're currently on is the 8.5. It's the most aggressive emission scenario. That's the one we're currently on. And you see they all sort of cluster together until about 2050, and then they spread out according to the realizations of a warmer world. But then you'll see this dotted line. This is a totally new realization in the AR6 report that came out last year. And it's called the low likelihood, high impact storyline. That includes this ice sheet stability that we just talked about. It's shown as a dotted line because this is the response of sea level that includes these, what we call nonlinear ice disintegration processes linked to rising global temperatures, in particular the ocean's role in warming the bottoms of ice sheets so that they can melt much more rapidly. And you'll see that's a completely different scenario. And it's one that has low likelihood, but just incredible impact, obviously way outside any of the other projections. Another way that the oceans are telling us to stay below 2 degrees centigrade, which is we're right now at about this range. We own about 1.5 degrees centigrade warming right now, even if we stopped emissions. We have another decade or two to curb emissions to stay below 2 degrees centigrade. But we really want to stay below 2 degrees centigrade. And this is actually one of the most profound reasons for doing so. And this is something called the global ocean conveyor. Some of you are familiar with the Gulf Stream in the North Atlantic. This is this warm ocean current that carries warm water from the tropics up to the poles. And it's actually responsible for about 50% of the heat transport. These currents, more broadly, are responsible for about 50% of the heat transport from the tropics to the poles. And you can ask the very good question, why does that matter? It matters because that's what makes the temperate regions habitable. And so this is actually one of the largest flywheels, one of the largest gears, if you will, in the global climate system. And so any small change in this means really dramatic changes in climate, not just in the region, but really worldwide. And this is actually something we've seen in the geologic record when we look at past times when this conveyor belt has slowed down or shut down even. And so one of the concerns is that as the oceans are warming, particularly the polar oceans, which are actually warming at a rate that's 3 or 4 times the global average, as they warm and as they become fresher because the ice sheets are melting and therefore having this freshwater runoff to the oceans, warmer, fresher water does not become as dense as cold, salty water. And so what's driving the conveyor today is this conversion of warm, salty water to cold, salty water. Well, today what's happening is the polar waters are warming and they're becoming fresher. So they're not becoming as dense as they were previously. And so this is starting to slow down the efficiency of this global conveyor. And what I can tell you is that this is just a fundamental part of the climate system. The last time it shut down was the time before about 12,000 years ago. Obviously, before there were any emissions, natural emissions, it's something that does happen naturally. But the last time it happened, just to give you an idea of just how profound this is, it's a very rapid process because either you float or you sink in this water parcel, and that hinge point is very non-linear. It's an on-off switch, basically. And so the temperatures in the polar regions change by about 20 to 25 degrees centigrade within the time it takes to finish a college degree. It's incredibly rapid. It's one of the real switches that exists in the climate system that we're very concerned about, just because it can throw in incredible uncertainty, not only to temperatures, but also to where rainfall occurs. So it can steer rainfall to or from the grain belts of the world. It shifts the rain belts in the tropics. It has a real global influence. Essentially, it just introduces uncertainty, and that's something we humans generally don't like. So to reduce these risks, negative emissions are required. This is a plot that's actually showing the rise in historical emissions from 1900 to today, to 2020. And you can see this increase. We're now emitting something on the order of about 36 gigatons, billions of tons of carbon per year. And that's been going up and up over the years. It's starting to sort of trend down or level off a little bit, luckily because of changes from coal to more efficient gas and actually expansion of renewables and gains in efficiency across industries. But we're a far way away from this red and purple line, which is the path we need to have to stay below 1.5 degrees warming into the future. This steep decrease in emissions can only happen by what's actually happening right now is emissions reductions in developing more efficient fuels and the like. But for the first time, because we've delayed for so long, negative emissions are required. And so it begs the question, what are negative emissions? Negative emissions are technologies that really don't exist at scale today to remove carbon from the atmosphere and durably store it away from the atmosphere so it can be kept away from the warming influence that would occur in the atmosphere. So these negative emissions technologies include things as simple as growing more trees, the afforestation technology. Essentially, growing more forests would allow us to capture more carbon from the atmosphere, not very durably, because trees don't last a long time. But there are other methods as well, which are actually much more durable. The key point is that we are now at a stage, because we've waited so long, that we have to deploy carbon dioxide removal technologies. And that's really where we're going to pivot in this presentation today, is what those look like. So why I think carbon dioxide removal is likely is really rests on the issue of urgency. So if you do an analysis of the global carbon emissions budget and ask how much time do we have before we reach this 2 degrees centigrade threshold, we have about a decade, maybe two, to get to that point. This does not mean the world is ending in a decade or two. It just means that we own a plus 2 degrees centigrade and warmer world if we delay that long for action. We really want to get ahead of this before that time. The scale of emissions is measured in billions of tons. We emit, all collectively, humanity emits about 10 billion tons of carbon to the atmosphere every year. So it's a massive amount of carbon. So whatever we do in terms of coming up with ways to remove carbon from the atmosphere, we're not talking about shrubbery. We're talking about very large scale technologies. And the best visual someone has shared with me is just imagine the current oil and gas extractive industry in reverse. That's the scale at which we're looking at. The other is the economic drivers behind this. The economic activity linked to carbon removal. If you just do the math, at the current strike price for carbon on the European market is about $70 a ton. We emit 10 billion tons a year. We're talking nearly $1 trillion a year per year of a new economy to take carbon out of the atmosphere once there's a price on carbon. So all of this hinges on that price on carbon activity, but already there's a $350 billion trading market for carbon in the European market to meet the Paris objectives. I also think carbon removal is likely because of the ocean. The ocean has tremendous capacity to take up the ocean. I'll get into this in the future slides, but the oceans may represent one of the ways in which we can accomplish this really daunting challenge, both at scale, with the urgency that's required, and at a price that's affordable. One of the most sobering lines in the IPCC AR6 report, this report that was released in 2021, is that all pathways that limit warming to less than or to 1.5 degrees C warming require carbon dioxide removal. This is the first time that that statement had been made. So it just really underscores the position that we're in right now, even as I'm giving this talk. This is something that's we've now waited so long that we really have no other option. We have to do this. It's unfortunate, but that's where we are. So the ocean has vast carbon storage removal. Just to give you an idea, the amount of carbon in the atmosphere, the ocean has 40 times that amount of carbon in the oceans. It does so through the dissolving of carbon dioxide into the surface ocean, through the crashing of waves and air-sea exchange of gases. And the ocean takes up that carbon, and indeed that forms the building blocks of life in the ocean. So one of the first ways that the carbon dioxide gets into the ocean is something called the solubility pump. The solubility pump is really just this exchange of gas from the atmosphere into the ocean through these crashing waves, very similar to how you carbonate a drink, how you have carbonated beverages, beer, soda, the like. That exchange of carbon reaches into the ocean, and because the ocean has a certain saltiness and alkalinity, it allows the ocean to take up vast amounts of carbon. So this is why the ocean has 40 times more carbon in it than does the atmosphere. So an expression amongst geochemists is that if the ocean sneezes, the atmosphere gets a cold, and that the ocean, very small changes in the ocean can control the content of the carbon content of the atmosphere. So this just shows actually where man-made CO2 enters the surface ocean around the world. This is a transect going from the North Atlantic around the Southern Ocean and into the North Pacific. And anywhere that you see is kind of red or magenta, you see it only goes down to a depth of about 1,000 meters in the oceans. The oceans are on average about 5,000 meters deep. And so really the penetration of anthropogenic carbon, of carbon since the Industrial Revolution, has really just penetrated the skin of the ocean, the upper 5 or 10% of the ocean. So most of the ocean has not seen the human carbon reach it yet, and we're going to get to that in a moment. The second way that carbon gets to the deep ocean, and really this is the way in which carbon is really brought to depths in the ocean, is through something called the ocean's biologic pump. So this is the process by which life in the ocean, like phytoplankton, form the base of a food chain in the ocean that then feeds all the way up to the apex predators, driving this cycle of life in the sunlit portions of the ocean. That's where we fish, that's where we get our food. And indeed, the oceans are responsible for every other breath of oxygen that we breathe. The variety of life in the oceans really drive this incredibly rich ecosystem. And what we see here is actually this flux of carbon that comes from the surface of the ocean. And then some portion of it, about 1% of it, makes its way down to the deep reaches of the ocean. So this is a way in that we see carbon making its way from the surface, the sunlit surface parts of the ocean, to the dark, midnight, and actually sunless depths of the ocean below 1,000 meters, 2,000 meters, all the way down to the seafloor. What's interesting is that if we actually were to image this subsea life, what we see is actually, it's almost like a wave. It's actually the world's largest migration on the planet. This is the migration of deep sea organisms that go from what's called the twilight zone down about a half a mile deep in the ocean where there's no sunlight. And then they come up to the sea surface at nighttime to feed and where they can be in relative safety. And then in daytime, they go back down again. And this cycling of life in the ocean is actually acts like a pump to capture carbon from the surface of the ocean and sequester it down at depth. If you turn on the lights, if you're able to look in the ocean, there's an amazing diversity of organisms there. Some of the largest diversity and numbers of small fish exist in the deep oceans. And this is really where you get this transformation of organic carbon that's raining down from the surface, from all the dead life that's making its way down through the oceans. There's a whole ecosystem below the sunlit region called the mesopelagic that gobbles up this carbon and processes it so that it can sink efficiently to the seafloor. So if you were to go down to the deep oceans, and this is actually an image from a submarine at about 1,000 meters water depth in the ocean, It's what Rachel Carlson called the most stupendous snowfall on Earth. And this is really this, if you flick on the lights, as shown in this video, it's basically just a snowstorm. Everywhere you look out, you see these particles, these white particles in a flurry. And what these are is these are the organic remains of fish and of plants and of other animals that have died and are sinking through the water column. And they've been partially eaten and they've been partially oxidized by microbial activity. And indeed, this is a big part of the global ecosystem. This is actually responsible. This process sends as much carbon to the deep ocean as we as a species emit to the atmosphere every year. It's a massive process. Indeed, if you were to shut this off, the carbon dioxide content in the atmosphere would double. So one of the ways that we look at this is that this rain of carbon from the biologic pump that reaches the old cold waters at the bottom of the ocean. Remember, the average depth of the ocean is 4 or 5 kilometers. The temperatures of the water there are at or near the freezing point of water. In some cases, they're below it. An important thing to remember is that the ages of the water on the bottom of the oceans, they are measured in the order of 100 to 1,000 years. So you can almost think of this like a bottle of wine that has been corked for 100 to 1,000 thousands of years. This is the last time this seawater in the bottom of the ocean last saw the atmosphere. And that's because the ventilation of the deep oceans by the ocean conveyor belt that we talked about, the AMOC circulation, that flow of water is very slow. And so when you get to waters, let's say off the coast of Hawaii, at depth in the bottom of the oceans off Hawaii, the waters there have a circulation age, meaning the last time that they saw the atmosphere was in excess of 1,000 years old. So if you could somehow increase the storage of carbon in these deep waters, you can durably store carbon for centuries to even millennia. And it may sound like a pipe dream or a bridge too far, but indeed, this is actually how the planet works. When we have drilled in the ice sheets of Greenland and Antarctica, we can actually look at the gas bubbles in the ice to determine the carbon dioxide content of past atmospheres of the Earth. And this is indeed how we know the natural variations of carbon cycles. And shown here in the dark blue is the carbon dioxide content of the atmosphere going back for 800,000 years. Now, this is based on a core in Antarctica, an ice core that was taken. This ice core shows that, for example, during the last ice age, about 20,000 years ago, the carbon dioxide level was about 180 parts per million, as opposed to what's called the pre-industrial number when the Industrial Revolution began, of about 280 parts per million. So it's fully, it's a full 1/3 lower than it is during a warm period. And you'll see it goes up and down this very regular pattern. These are the ice ages. There were many ice ages. You can see there, in this case, there was something like a dozen ice ages. There's actually 40 if you go back in time. And there are lots of warm periods, but you'll see there's this envelope of variability between temperature and carbon dioxide, and they go hand in hand with each other over this 800,000 year period. The key reason for me showing this slide and telling you about this is that the oceans and the atmosphere have this natural dance, if you will, that exchanges carbon between the atmosphere and the oceans. And this has been a leading cause of climate change going back into the past. What's different today is that the carbon dioxide level is around 450 parts per million now, or 430 parts per million now. It can't even be shown on this plot. It wouldn't even plot on the slide. It's so far, so high. And so the temperatures are chasing that carbon dioxide extreme. But the reason for these past historic changes in CO2 were changes in the ocean storage of carbon dioxide. And that's really the reason for showing this, is that this shows kind of the lungs of the oceans as they take up carbon naturally and release carbon naturally to the atmosphere. So we can take that knowledge and say, well, how can we look at ways in which we can understand how the ocean can naturally take up carbon in excess of what it's already doing to naturally store it in the deep oceans. as stimulated by some man-made process. So there are lots of ways to do this. There are something like 20 different technologies. Indeed, there was a National Academy study that just came out a couple of months ago that explored 7 of the most promising ideas. This is one of them. It's called iron fertilization. In a nutshell, it involves using trace amounts of iron of iron sulfate on the surface of the ocean, and it stimulates like a fertilizer. It stimulates immense productivity. And so this slide here on the right hand shows actually a deliberate release of iron into the ocean. And that green donut that you see in the ocean is 100 kilometers in diameter. This is actually an image from a satellite. The green is excess chlorophyll, so it basically means stimulated primary productivity in the ocean. And so this is a way in which one can stimulate greater productivity in the ocean. And the idea is that if you stimulate more productivity in the ocean, more of that carbon makes its way through the water column into the deep sea for durable storage. Just to give you another idea, another example that is out there is for intentional kelp farming and actually developing these bales of kelp and sinking them in the deep ocean. Again, it's cold and deep in the deep ocean. And so it's a way to store many, many tons, gigatons, billions of tons of carbon in the deep ocean. Now, none of this has ever been done at scale, but in principle, these ideas work. A very interesting fact, I think that really frames this is to understand the ocean's potential to take up carbon. One could take the entire volume of mass of carbon released by human emissions since the beginning of the Industrial Revolution by all countries up to the present day. One could take that entire inventory of carbon, and if one mixed it uniformly in the ocean would barely even know it. It's about 1% to 2% of the total carbon budget of the ocean. The take-home point here is that the ocean has tremendous capacity to take up really large volumes of carbon. And what we don't know is what happens is if one intentionally pursues that and how that impacts ocean health or ocean function. And that's really where we're going in the next few slides. So as I mentioned earlier, that the National Academies just released a report on ocean CDR, ocean carbon dioxide removal. It's a whole research program. It's almost about an $850 million proposal to the US government to invest in research to understand how the ocean can uptake carbon. So this is not only an initiative here at the Woods Hole Oceanographic Institution, but really this is a much larger effort really across the nation and indeed around the world, again, because of the ocean's tremendous potential to take up carbon. So it's here where I really take a break and have a moment of humility to say that really science's role here is that we have to stay ahead of solutions. I don't want to be in a position of advocating for doing this or not doing this, but really the science and our understanding of the ocean's response to these kinds of actions, we really need to develop the capabilities to monitor and to track that process. So I begin today with inviting a new era of ocean exploration. We do not have the observational capabilities, despite our advances in robotics and the rest. We do not have the capabilities right now to monitor this process or their impacts on the oceans. We need to use this enhanced exploration to understand how the oceans will work, how they are changing, and what the unintended consequences of ocean CDR might be. So we here at the Woods Hole Oceanographic Institution have commenced on a grand challenge that's engaging our 1,000 scientists, engineers, and marine operations specialists. We're focusing on developing this three-dimensional ocean data cube, if you will, that's twice the size of Texas, so it's 1 million square kilometers or 1,000 kilometers on a side, going from the surface of the ocean all the way to the bottom. And the idea is to basically build something equivalent to the Hubble telescope, but for the ocean, to let us understand what's happening in the full volume of the ocean at the scale at which they're happening. Right now, we have occasional samples here and there with year-to-year variations, and many of the places we don't even visit. Only about 20% of the oceans have been explored. We've never had this kind of a detailed understanding of the ocean ever. And so the idea here is to develop this always on, always connected ocean Internet of Things to measure ocean health, ocean function, and particularly to focus on carbon flow. So here, this is depicting this crisscrossing arrays and armadas of gliders, of autonomous vehicles, of moorings, and acoustic sources, light sources, essentially ways to understand the processes that are happening below the surface, both in space and time. And so if we were to think about the application of this to the ocean carbon CDR that methods that we discussed earlier, it might look something like this, that as we start to explore how the oceans are behaving, then if we were to do deliberate experiments to enhance the biologic pump, for example, we can measure this and we can monitor this. We can determine whether this is having a net positive or net negative or a neutral effect on the oceans. Right now, we have no such capacity. Just given what I see as the gold rush towards solutions coming to the oceans, I think it's just really important that science has to get ahead of solutions to understand these impacts. So if one were to ask, well, where would you deploy this? The first thing is we have to conceive of how to do it, and we have to show that it works. And that's really the work that we're beginning at the Oceanographic today. Where we can deploy this is really almost anywhere in the ocean. This slide shows that if you were to have a deliberate enhancement of primary productivity in the ocean, what fraction of that carbon that's sinking through the water column would be durable, would be stored for greater than a century. And you can see that if you can get it below 1,000 meters in most of the ocean, you can store it durably for a century to over a millennium, particularly, let's say, in the Pacific Basin. So I see this as really an opportunity for really exciting challenges for the ocean science community, and indeed for all of the earth science community, is that, how can we exploit models and observations to advance our understanding? Where would it be safe to operate these kinds of ocean CDR technologies? How big of a signal can we detect? How far do we need and how long do we need to measure for to get a clear understanding of the process? What would be the fingerprints to document the efficiency of this? And then, how accurate can we get this? What is our ability to define the accounting of ocean CDR? This is what's fundamentally important, is that if someone's going to be paid $100 a ton to store carbon in the oceans, we have to prove that it's actually being stored and that it's not causing harm. So this is just a nutshell, just sort of a comment on the Oceanographic. This is exactly what we do. We have a really large team of technicians and engineers that design these sensors and probes to work on this very process. But we're just one organization within a global consortium of oceanographic institutions that could contribute to this effort. So I'd just like to wrap this presentation by offering these takeaways. We are now at a stage where we're in urgent need of solutions to the climate crisis. We have really, our window of time to act is measured in years and not in decades. We believe that the oceans serve as a really major opportunity for us to explore climate solutions. We can explore and understand these ocean-based options for capturing carbon. But first and foremost, science must stay ahead of solutions. Fundamentally, our role in society is to understand how the oceans work and how we can understand the ocean's ability to help avert this crisis. But again, we have to really understand how the oceans are changing, and that requires essentially an Apollo-like program of new discovery, of new exploration of the oceans. And that's what we're pursuing here at the Woods Hole Oceanographic. So with that, I'd like to end my presentation and say thank you very much for your attention and your time today. And for those of you who would be interested, I invite you to write to me here at the Oceanographic. I'd love to entertain your questions, or perhaps even welcome you to the oceanographic here in Massachusetts. Thank you very much for your time.